In this video, I'll be demonstrating a method to calculate the distribution of rays on an intermediate plane during a ray trace. So for example, if I go ahead and poke the ray trace button on this triplet system, I've got a little filter sitting in between the second and third lens elements. You can see that the rays are for the most part, exiting the system or ending at the end of the ray trace on the detector surface, which means that if I wanted to look at the distribution on a plane at the end of the ray trace, my choices are pretty much the detector surface, because Fred by default doesn't keep track of the intersection positions during a ray trace on a specific surface. So what we're going to do in the scripting language is we're going to use Fred's advanced ray trace to step the rays one intersection at a time through the system. So for example, surface 1, lens 1, surface 2, lens 2, etc., 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 down the line. At each intersection, we're going to loop over the rays and say, do you exist right now on a current surface of interest? If you do, we're going to place a copy of that ray into what's called an auxiliary ray buffer. So you have your main ray buffer where these rays exist. For example, if I hit the ray trace button, we can create a number of auxiliary secondary ray buffers. So each intersection, do you exist on a surface that I'm interested in? If you do, we place you in a unique ray buffer to that surface. And then at the end of the ray trace, we can select the ray buffer for that specific surface, and when I perform the analysis, only those rays that had intersected that surface during the ray trace will be included in the analysis. So we're going to do this through the scripting language. Let me go ahead, I have two embedded scripts here in this sample file. The first embedded script is going to be run to create the unique ray buffers for each surface that we're interested in. The second embedded script is going to, after the ray buffers have been created and the ray trace is completed, is going to bring up a user-defined dialog that will allow us to pick the surface that we want to perform the intermediate analysis on, or delete all of the temporary ray buffers that we had created. So let's go ahead and look at the script that creates the ray buffer. First block of code here does some cleanup. If there are any temporary ray buffers, we go ahead and just delete them. The second block of code here, you can see, has a key command called isEntitySelected. What this command does, this is useful for a lot of scripts, utility scripts. If I go ahead on the object tree here and say I selected these three surfaces, the isEntitySelected command, if I loop over the entities on the object tree, is going to check these surfaces and say, are you highlighted? If you are, then we're going to do something. So that can be really useful in a number of applications. In this case, we're using isEntitySelected to identify those surfaces on which we want to perform the intermediate analysis during the ray trace, so beam footprint, for example. In the first part, we're using this loop to get the number of selected entities, and then in the second loop here, we're going to create a unique ray buffer. You can see the add ray buffer command. So each selected entity, if it's a surface and it's selected, create a unique ray buffer for it. Next, we set up the advanced ray trace, and you can see that we've used the hit count member of the T-advanced ray trace structure. We specified that as 1. So what we're going to do is step each ray one intersection at a time through the system, and then we're going to loop over the rays to perform some checks. So here's the do loop. What this block of code will do is it says do until the number of rays equals 0. What is number of rays? Well, number of rays is the function returned for the advanced ray trace call. If any rays are allowed to be traced, then it's going to return a number greater than 0. If all the rays have finished their lives, that is, they can't be traced any further, number of rays is going to be 0. In that case, we exit the do loop. So this ensures that all the rays have made it to the end of their lives, so to speak. During each step of the advanced ray trace, we're going to loop over each ray. So this is a typical while loop. We're going to loop over each ray. If it's on the entity, if the entity that the ray is on is one of those that we selected previously, so for example, we had created the B nodes array here when we did isEntitySelected, so each element of the B node array got a unique ray buffer. If it exists on one of these surfaces of interest, and its number of intersections is equal to the number of steps that we've taken in the advanced ray trace, then we're going to copy that ray to the ray buffer. The second part is important because a ray could have ended its life on that intermediate surface, and we don't want to make multiple copies of it in the ray buffer, so we just want to copy it one time. Okay, so that's the first script here. Let's go ahead and run that on our system here. In this case, I'm going to be looking at surface 1 of the filter here. You can see it's right here in the 3D view. I've already got an analysis surface there. If you want to look at multiple surfaces, you're going to have to create more analysis surfaces and place them in the proper locations here. So I'm going to look at surface 1. Let's go ahead and run our embedded script. You can see printed to the output window, it deleted old ray buffers, it created a unique ray buffer for the surface of interest, and it started the advanced ray trace, and it took 25 steps. So let's go ahead and look at the second embedded script here. This script is primarily providing some user interface to choose the ray buffers that we've just created. So we go ahead and loop over the ray buffers that exist in the document, and we provide a user dialog where the user can select from the ray buffers which one they want to look at. Remember, each surface of interest has its unique ray buffer, or we can delete all of the temporary ray buffers that we've created. We're using here this get full name of ray.entity to identify the surfaces that we selected initially, because remember, each unique ray buffer only contains rays that existed on that surface, so we just query the first ray in that ray buffer to get the entity name. If the user has selected to delete all temporary ray buffers, we loop over the ray buffers that exist using getRayBufferCount, and we delete them. Otherwise, we can go ahead and set active ray buffer equal to the ray buffer that the user selected. So let's go ahead and run this script to see what the interface looks like. Remember, you can write custom dialogues in WinRAP. So here's the dialog we created. We have two ray buffers, the main ray buffer, which always exists, and the unique ray buffer that we created for filter surface 1. So I want to select filter.surface1, hit OK. What we've done now is if I perform any analysis, it's only going to use the rays in the filter.surface1 ray buffer. So I've got my analysis surface on filter surface 1. I'm going to go ahead and do a positions spot diagram, and here's the beam footprint during the ray trace as the rays pass through the filter surface. Now I want to go ahead and delete the ray buffers that I've created. I'm going to run my second script again. I'm going to say delete all of the temporary ray buffers. You can see it printed to the output window that it deleted all the ray buffers. So what does it look like if we've selected multiple surfaces? Remember, you'll have to add some more analysis surfaces at these locations. Go ahead and run our first script to create the unique ray buffers. So I've selected 4 surfaces. I'm expecting a total of 5 ray buffers, including the main ray buffer. Now I'm going to bring up my ray buffer dialog here. I can see main ray buffer 1, 2, 3, 4 unique ray buffers. All of these ray buffers containing only rays that passed through that surface during the ray trace. You'll be able to find this file and others on our knowledge base. We've included some documentation to explain the scripts and the implementation. It's called Multiple Ray Buffers. Feel free to download these documents, play with them, and please send any questions or suggestions to support@photonengr.com.